we're still very far from answering this question, like how does ChatGPT work internally? I mean, nobody really knows how it works. I can tell you just kind of how it works, maybe on a very high level.
You're about to see a conversation with Alex Makelov, one of the very few people who studied at Harvard, Cambridge, and MIT. First, Alex was a very strong competitor in math and physics, and he represented his country Bulgaria in both subjects. Later on, Alex became computer scientist after enrolling in the PhD program of MIT. The WAP of Alex at MIT was specializing in large language models, and around the end of our conversation, Alex is gonna tell us about some lesser known things related to ChatGPT. So stay with us till the end. This is the lesser known math channel, and currently the only way to support it is by subscribing. So please do that. Now let's enjoy the conversation with Alex Makelov. All right, so welcome, Alex. It's very nice to have you here.
Good to be here.
I will be glad to ask you some questions about your past, the very interesting things you've seen in the math/computer science world. First, let's go quickly over your high school years. You represented Bulgaria as part of the national teams in two major subjects, math and physics. However, later on in your PhD, you did computer science. Can you tell us about this transition? How did it happen?
Yeah, sure. So, well, I really started seriously doing math in the 5th grade. So, yeah, so math was my first academic passion, I guess. So, yeah, I'd say math is like the main thing in some sense. And then over time, I've kind of added a few things to it. I think in 9th grade, I just heard about physics olympiads from my high school teacher, Zhivko, and I'm really indebted to him for just showing me this and being like, oh, we should just go to these olympiads and helping me prepare. And yeah, and then after that, I just started going to these competitions and had a lot of fun also doing physics. And I was also from before then I was also going to math competitions. And yeah, and that was like in high school, I was mostly doing math and physics. So computer science wasn't really on the radar much. And then when I got to college, I was still doing math mostly. And I took some physics, but then I thought, maybe there's more things to do in math, or slash I felt I was more interested in the things in math. So I kind of dropped the physics part at that point. And then as I was doing more math, I discovered I like discrete things more. So like combinatorics and things like that. And this kind of naturally led to my interest in theoretical computer science. So in my undergrad, I did a bunch of theoretical computer science, which is kind of mathy computer science with like almost no coding really. And yeah, and I was pretty happy doing this for a while. And then eventually in my PhD, I had a lot of back and forth, I guess, between like if I want to be more theoretical and more practical, but eventually was leaning more towards doing more practical stuff. So this is where the machine learning kind of came in.
How did this happen? Like all of a sudden you start to be interested in more practical things, deep learning and stuff. So was the reason huge applications by themselves or something else?
Yeah, I certainly felt there was more potential for applications in machine learning because eventually, well, it's not completely obvious, but I think it's very plausible that eventually there's going to be some form of very strong artificial intelligence. So it was clear to me that in some sense, these things will be valuable down the road. It just wasn't clear how long it's going to take. So yeah, so this was, I think, a major part of the reason. The promise of practical usefulness, I think. I mean, you can, of course, do math if that's your thing, and it's like very beautiful, and there's practically infinite things to do there. But yeah, just missing the connection to practical things. And I really think that the thing I'm most excited about really is practical theory in some sense. So this is kind of the holy grail, I think. Yeah.
Yeah, this makes sense. And Was that also the reason for you to pick this topic for undergrad thesis related to expanders?
A little bit, I think. Yeah, I
Yeah,
mean, I think it's been like a
yeah,
bit of a gradual transition in some sense.
yeah,
Yeah,
yeah, yeah.
yeah,
So
yeah.
this kind of thinking about combining applications and beautiful theory has been in your mind
Right.
early on.
Yeah,
Yeah,
yeah.
I guess. Okay, okay. And then can you maybe distinguish some qualities that make the math people different from the physics people?
One thing is in physics, there's a bit less emphasis on rigor. I mean, I don't mean this in a negative way, but I mean more like in physics, it's often the case that you need to do some intuitive judgments about like a particular scenario that you're analyzing, and there's like different heuristics that you adopt. Like you have to ignore certain things, you have to approximate certain things, and really it's impossible to analyze like a complex physical system in complete detail, so you have to do these things. And in math, it's of course very different because you expect it to completely prove whatever you're trying to prove. Like you have to have a logically sound argument for everything, and this also includes the math olympiads, of course. And I actually found like this way of thinking from physics that's kind of like high level, large scale, kind of spotting like trends and asymptotics and things. I've also found it useful in certain math problems. So it's yeah,
Do you
and
mean
also
more to focus on intuition? Yeah, what's gonna happen at the end instead of just looking at small details?
yeah, this kind of thing, yeah, it can be helpful. Yeah, I think there's useful things to learn in both. Like the physics people can learn useful techniques from the math people, I think, and the math people can learn some useful ways of thinking. The other difference I've noticed between like math and physics contestants is the people who go to physics Olympiads, they really like tinkering with stuff, like actually, making things, just like doing actual experiments, in the real world, which is not something that's really a big part of math. um, because math is very like a priori, right? Like you just sit down and you think. So it's very different. And in physics, you can actually interact on a much more tangible level with the things that you're thinking about. So yeah, that's another thing I've noticed. Like these people love, yeah, just making things, experimenting with things, like electrical
Yeah.
circuits and like other like mechanical or optical things. And that's also maybe part of the training as well, because you have in physics Olympiads, you have to do these experiments. Like if you're competing at the international level, like usually there's going to be some experimental portion of the problems, and you have to, be able to do these things. So it helps to be a little bit of a thinker. Yeah.
Yeah, I've heard from several mathematicians some sort of, jokes or criticism about physicists that there is not enough rigor there. I mean, all of us have heard that, but are there these other kinds of jokes from the physicist about mathematicians that,
Oh
I
yeah,
mean,
of course, of course. I mean, it's usually something along the lines of how, yeah, like math actually doesn't, accomplish anything in the real world or things like that. Like that's
yeah,
usually
yeah,
what people joke about. It's the
not practical. Yeah, yeah,
classic high school banter. Yeah.
right.
But of course, yeah, it's much more nuanced than that. Yeah.
Yeah, yeah, sure. Then let me ask you about all these competitions you took part in. You're one of the few people who managed to be in the national teams of both math and physics. My question, I guess, is it more nature or nurture when it comes to success on these Olympiads in math and science?
Yeah, I certainly think nurture has a pretty big role to play in the whole thing. And this is partially because of the way things are set up, also, like in the Olympiads. These Olympiads have been going on for many years now, right? Like 50, 60 years,
Right.
I think. Over time, the problems are in some way getting more difficult because of that, just because people already know, all the tricks from the past. So
Inflation in everything.
so you have to, yeah, so you have to be aware of the tricks in the past to be able to do a decent job, or not always, but I think definitely helps to have some preparation. And yeah, this is where the nurture part comes into it, I'd say.
Yeah,
And at
you
least in
you have to
Bulgaria,
be
yeah.
very motivated, right? That's the key thing because
Also that. Yeah, this I think is a different part of it. Like there's multiple parts to the whole thing. Preparation and just having access to the right resources and to people who can actually help you prepare. I think that's one part. Yeah, as you point out, motivation is another part, which is not completely clear to me how it works exactly.
yeah, it's complicated because the better you are in these competitions, you have the stronger motivation.
So it's important to also have a support system in a way of like, or like a system of, you know, competitions in your country, like nationally, locally, not just, you know, internationally, so that this keeps you kind of in shape. This gives you constant feedback. This is also very important. And fortunately, in Bulgaria, we have very good resources. I think nurture in this sense, in the sense that I described, I think is very important. Yeah, the motivation part, there has to be a system of competitions that are frequent enough for people to be getting this feedback. But also another part is just people's own intrinsic motivation. Like, do I find this interesting? Like, do I find it rewarding to think about this for hours or not? I think this makes a big difference. And this is less clear to me how it works exactly. It seems some people just enjoy this stuff, some other people just don't, but it doesn't mean that it's nature. It's not clear.
In relation to that, can you say something about this danger of, you know, just being focused as a kid on competing and just winning instead of developing knowledge in the right way and studying things that interest you instead of just solving questions in order to learn the tricks and be successful? I don't know, some kids, including myself to an extent, didn't realize at that early age that math is interesting for its own sake, and the actual final goal is just to get more in-depth knowledge. I think it would be much better if these students kind of realized early on that the final goal is just getting better understanding of the subject.
Well, I mean, yeah, I don't see why it can be both of these things at the same time. Like you like competing and you also just enjoy the math for its own sake. Like there's no contradiction between these two things. And for me, it was like that. Yeah, maybe not for everyone though. So it's probably some truth to that, what you're saying.
Yeah, I guess the issue is more that you're very young, but you're put constantly in some kind of stressful situations because you have time limits and you know it depends how you would perform. Otherwise, you're kind of ashamed from your peers.
I see. Yeah. Yeah, it seems some people don't like the time pressure, but they can still do pretty good work. So yeah, some people just don't like that, and that's fine. There's also other things to do, like other sorts of research where you're not really there's no one, you know, sitting next to you with a clock and just waiting for you to produce some research result. So yeah, I think it's very important to have both of these options. Yeah, I think in Bulgaria, it at least used to be the case that competitions were the more prevalent option, I think, compared to other research opportunities for high schoolers, because I mean, it's difficult research program for high schoolers. It's not, you know, it's not easy because you have to be very
Mature, maybe.
you have to be very you have to, you know, be a very good teacher, and also you have to have a very good choice of problems that you can give to people. But yeah, I definitely think it would be useful to have more of this other kind of opportunities also. And also going back to the thing about just doing it out of intrinsic interest in mathematics. I think it also depends on the teacher to a large extent. Like, I mean, if your teacher is just being like, oh, you know, you have to go to these olympiads because of it's going to help you achieve X, Y, and Z, which have nothing to do with mathematics, or that's creating one kind of attitude. If you have a teacher who's like, oh, you know, at the end of the day, what really matters is that you actually learn something, and that you find that you find out if you like this and if you want to keep doing it or not. And this creates a different attitude. And I think teachers have a lot of leverage here. For example, in physics, we had this very famous physics teacher in Bulgaria, right? Teo, as they call him. Of course, he would teach physics, like, because he has to, but he also, just tells stories about what people do with physics, in the real world, like how it's being applied and what kinds of like what kinds of jobs you can do, what kinds of impact or benefit to society you can have by studying physics. And I think it's very important for people to connect the dots and like have some motivation that's beyond just scoring like full marks on some test, which I think is very important.
Let me ask you at the end on this topic. If you have kids in the future, would you try to make them competitors, math maybe, or other subject?
I certainly wouldn't try to make them competitors. I guess I would just try to see if, or like, yeah, I think the best way to go about it is just to expose them to a whole lot of different things and just see, what they have an actual interest like an intrinsic interest in.
Yeah.
And just help with that. But I mean, if it happens that they have an interest in math Olympiads, then great, because I can help, right? And if not, then there's no point really forcing it. So yeah, I think that's my take currently. Maybe that's a bit too hands-off. I don't know. But it's also hypothetical. So yeah, maybe, ask me again in 10 years or something.
Yeah, many of today's moms would disagree with you, and they would think, yeah, your approach is indeed too hands-off. And then let's move on to your college years. Yeah, you chose to continue at Harvard after high school. The first thing I want to ask here is, did you need to do many extra things to get in addition to the international Olympiads you had?
Yeah, I think it was mostly the Olympiads. I don't really know what fraction of admissions are based on Olympiads and things like that. Like, it's not very clear to me if it's very high or low. Just based on my experience, there's a fair number of people from the Olympiads at these places.
Yeah, it depends also on the place, of course. For example, MIT is famous for admitting more people with Olympiads.
Right. Yeah, I'm sure it depends also on the place. Yeah. Should this be the case? Yeah, that's a good question. I think personally, most of the people I met through Olympiads were just pretty high quality people academically, I'd say. So I definitely think there's some signal there. It's not the only signal though, which is of course why they don't completely base their admissions on Olympiads, right? But it's kind of hard to quantify. Should it be less? Should it be more? Yeah, I'm not really sure. It's not a very data-driven answer. So yeah, but that's I'd say it is a useful signal.
Speaking of that, why did you choose Harvard?
So obviously reputation is good. So that's one thing. Another thing was they actually had pretty good math program. Like, before applying, I had no idea, but when I actually looked up like how well they do on the Putnam, for example, I saw that they're actually very good. So that was another thing, I guess, because at the time I was still very Olympiad focused. So to me, that was at the time an important signal. Like, nowadays, maybe not so much, but yeah. One thing I didn't appreciate at the time of applications though was that their math program also does not include a lot of combinatorics. So yeah, I did not know this at the time, but maybe this would have changed things a little. I'm not sure. Yeah, I think these were the main factors. Yeah.
Were you wandering between Harvard and another major place back in the days?
Yeah, I had to choose between there and MIT and Stanford. But I mean, obviously, all are pretty great places. So I don't think they would like a wrong answer here, really.
Yeah, definitely. Yeah, so my next question was prepared to be about, some general advice you could give to high school students who compete in math or related subjects. Yeah, so do you have any such advice?
I mean, one piece of advice would just be, make sure you're doing this for the right reasons. Like, make sure you're not stressing yourself out too much, because this can actually make just performance worse. So it's very counterproductive. Yeah, just make sure you're doing this because you're really interested in it. Because after graduate, there's not that many competitions anymore. It's like not really such a big deal after high school. There's still some competitions, but gradually as you grow older, there's like fewer and fewer. Like there's no math olympiad for PhD students, as far as I know. For example,
That's
my
a good
other
point. Yeah, it shows that yeah, this is definitely not the end goal, to
yeah,
become
exactly,
the best
exactly,
competitor in the world.
exactly.
Yeah.
My other main bit of advice would be to just read more widely, maybe, or not. Don't overfit to the specific material for the Olympiads. Yeah, just try to get a more general idea of, research beyond Olympiads. Like Olympiads can certainly help you for research. I think there's a lot of overlap in the skills involved. Because really it's about problem solving at the end of the day. So they're definitely very helpful, but you should also have some more, like some broader idea of what's out there and what research directions exist and what they're ultimately trying to achieve. I think could be useful. I mean, don't overdo it, obviously, because you're still in high school, but having some more general awareness, I think could help down the line. Yeah.
Yeah, great. Yeah. I like this advice a lot. Okay, and then yeah, maybe let's discuss a little bit your years at Harvard. Many people say that these top colleges are like, I mean, the education itself is not the greatest benefit, but it's more like the network you create there and the people you meet.
Just certainly to some extent it is the case. I think it very much depends on what you're majoring in. So if you're majoring in something that's more about business or politics, I think that's overwhelmingly the case. If you're majoring in some more like STEM subjects, it's nice to have friends who do the same things and who do good work. It's very important to actually understand things deeply. Like I think at undergrad, that's kind of your main goal should be to if you want to research afterwards. Your main goal probably is to just understand things very deeply so that you can be able to participate in research later. And this also happens by having a network, right? Because if you have a lot of people to talk to who are taking classes with you, then that helps. So you can learn from them.
Yeah,
And
but I agree that in STEM, the network doesn't help maybe that much because, yeah, you can just read the book yourself, even if you're in another school.
yeah, it still helps. Yeah, it still helps somewhat.
At the end of your college years at Harvard, you chose to write a thesis about expansions of lifts of graphs. Yeah, you even got special prize for undergraduate thesis, I think, at Harvard, which is impressive. You can tell us some words about this thesis, the topic, how you chose it.
Yeah, so regarding the prize bit, just to get it out of the way, this is a prize they give to a lot of theses, I think. I'm not sure how many, but it's not like, only one person gets it or something. So I don't think it's like extremely prestigious or anything. I think you just get nominated by whoever is advising the thesis, and then there's some selection process. Yeah, I don't really know. Like I didn't think much of it at the time. But yeah, the thesis itself, yeah, it was just something that I found very interesting. I was doing some research with Professor Solovadan. He just told me about these things called expander graphs and how they have all these counterintuitive properties. And I was pretty fascinated by this, so I wanted to understand more.
Since we are in a math-related channel, maybe we can go more in depth here. As far as I know, an expander is just like kind of a sparse graph which is well connected, right? Roughly speaking.
Right.
So do you mean that when you say counterintuitive properties?
Well, they have many different surprising properties because there's many different ways to characterize expanders. Let's see. What is the most surprising? I'm trying to remember. Put me on the spot here.
It has been a while. Yeah.
Yeah, it has been a while. One surprising thing, there's many surprising things. One of them is they allow you to de-randomize algorithms, one of their applications. Well, it's kind of a theoretical application in some sense, but it's like theory being applied to another part of theory. So so for this de-randomization, you'd have some sort of randomized algorithm, and this randomized algorithm actually needs to use randomness. So you have to flip some coins or whatever to generate some amount of randomness. And then in complexity theory, it's about quantifying the resource requirements of algorithms, right? So it could be time, that's the most familiar, I guess, to most people. It could be space requirements, and it could also be randomness requirements. So you can think of randomness as a resource because it takes some work to generate randomness in some sense. That sounds kind of weird, right? But if you want to make sure that you have high quality randomness, which I'm not going to get into what this even means, but there is such a thing. So if you want to get high quality randomness, you have to spend some work. And yeah, people in complexity were interested in quantifying the amount of randomness to achieve certain tasks. And I believe it's still open. It's still an open question if you need randomness at all, in the sense that a lot of people, I think, believe even that the class P of polynomial time computable functions or languages or whatever is actually the same as the class of things you can compute in polynomial time if you also have randomness. And yeah, and people have been trying to prove this for a long time, and I don't think they've been able to so far. But one line of work in this direction is de-randomization, which is reducing the randomness requirements of some algorithm. And this is where you can use expander graphs. And yeah, and you can have some algorithm that needs to flip like thousands and thousands of coins. And you can somehow use these weird graphs to make it so that you can actually get away with flipping just a few coins, like 10 coins or whatever. Yeah, and this was pretty surprising. And the reason this happens just on a very high level is, as you mentioned, these graphs are very sparse but very well connected. So this means that if you start at some vertex in this graph and you take just a few steps, you can end up in a completely different part of this graph. And this is kind of how it's used for de-randomization. So you can think of this randomness that you're generating as sampling random vertices in your graph. And then it turns out that instead of like sampling a random vertex every time, which takes a lot of randomness because you have to choose from the full set of vertices every time, you can just pick a random vertex to start from, and then you go along the edges of your expander. So you take a random walk in your expander, and this random walk is also pretty random because this graph is so well connected, so you can end up anywhere basically. And at the same time, it needs less randomness to specify this random walk, because after you choose the first vertex, each next step requires you to choose just one of the edges leaving this vertex. So instead of choosing from all the vertices in your graph, you're just choosing which edge am I going to take next. And because these graphs are sparse, as you mentioned, this is much fewer things to choose from, so it's much less randomness that you need.
Oh,
so that's one application. And yeah, it was pretty surprising when I first saw this.
Okay, so next you moved to Cambridge to do the famous Math Tripos masters, right? Which involves just taking lots of graduate courses of all kinds related to math, and then you have this notoriously difficult exam at the end. Yeah, maybe just tell us how come you chose to move to the UK then, and what was your idea when you made this step?
Yeah, I think part of it was I just wanted to check out what it's like in Cambridge. Yeah, the program itself, as you said, it was just a bunch of courses, so I mostly took combinatorics. Yeah, fortunately they drop your lowest exam score, so that was helpful. What did I do? I think mostly like probabilistic combinatorics and some graph theory, because I thought at the time that I would just be doing graphs for my PhD like the entire time. Yeah, my overall impressions. Well, I mean, it was very different there compared to Harvard, because at Harvard there's very little combinatorics happening in the math department, whereas at Cambridge there was a lot. So there were a lot of prominent people doing Yeah, all sorts of combinatorics there.
Timothy Gowers and
Right.
Imre Leader, right?
Yeah, and Bela Bolobash
Bosch
there
is
at the
there,
time. Yep.
right?
And Andrew Thomason. Yeah, the exam focus was very different also from the States, I think, because there, or at least
More,
at Harvard, it's very uncommon to have like actual exams for such high level math classes. It's usually something else, or sometimes even nothing, like just a bunch of problem sets that you do, and that's it. And at Cambridge, it was very different because like nobody forces you to do anything for the semester. It's just these exams at the end, and you have to take them.
yeah, anything else regarding differences between Harvard and Cambridge, maybe in terms of environment, people?
Yeah, I think Cambridge is much more spread out, just the campus. And there's all these colleges, right? And it's more difficult, I guess, for people from different colleges to hang out together just because the distances, I think.
Yeah, the which campus did you like more in terms of, architecture and atmosphere?
Well, that's a good question because in Cambridge they have all these colleges that have their own like gardens and stuff, and they can be very picturesque. And Harvard is more urban, I guess. I think
I see.
architecturally Cambridge was more impressive.
Yeah, it's older as well.
Right.
What happened on this famous final exam? It has like 200 years of history, I guess. The exam itself for the Tripos.
Okay, well, I'm absolutely sure, first of all, that there was an exam for each subject you take. So you take a bunch of subjects, right? And then
Yeah.
for each subject, there's an exam. And it's usually maybe 3 hours or something like that. Two, three, maybe, I don't know, maybe sometimes 4 or 5. I don't remember. I think it depends on the subject. Like, I think the professors can just choose how they want to set it up, I think. And then yeah, and it's I think that the toughest part of it is that it's all in 1 week or in like a short amount of time, basically all the exams. And these are like final year exams. So after a whole year of studying things, you have just one exam at the end, and all these exams are basically in the same week. So that's kind of exhausting, I'd say. Yeah, otherwise the exams were just normal exams, like nothing super weird happened. I don't think.
Yeah, but
Yeah.
then at the end they do some kind of ranking, right, of the
Oh yeah, yeah,
people.
yeah.
And I also heard there are some famous tutors preparing people for exams, right? And
Oh really?
this,
I didn't run into that.
yeah, okay. I didn't interact with such.
No.
Yeah,
One
yeah.
thing that I noticed about the exams was that I guess you really had to be prepared, or like you really had to remember a lot of things in order to just be able to do it in time, I think.
Yeah, when I came to the US, for me it was also kind of a shock because yeah, the exams here are very strict time limits and tight time limits, I would say.
Mm-hmm.
Whereas
Mm-hmm. Right.
yeah, in Europe it's more like yeah, you have 3-4 hours exams more frequently, I think,
Mm-hmm.
for small number of problems, it seems. Okay, and then you move back to MIT, but this time for PhD in CS. So I guess during that time you wanted to do theoretical CS. Yeah, you decided to go back to Boston. Maybe you had some sentiment about the old days.
Oh well, actually the decision to go to MIT was made before going to Cambridge. So
Oh wow.
right. So I already knew that I was going to MIT, so I deferred for 1 year just to go to Cambridge. Yeah, no, it was a wild time. First years of PhD, because so first of all, yeah, I didn't really know exactly what I wanted to do, and second of all, deep learning was coming up at the time, and my lab was originally doing like more theoretical stuff, optimization and so on, but just switched to deep learning pretty fast.
Oh, the
Um,
whole app.
almost the whole lab. Yeah.
Wow. We can discuss some specifics about your work now. I saw some interpretability papers, stuff like that, but yeah, maybe you can tell us more.
Right, right. Yeah. So currently I'm doing this thing called Maths, which is an independent researcher program where they pair researchers with mentors from industry labs that are doing machine learning. And now I'm currently fortunate enough to work with Neonanda, who's one of the best people out there doing interpretability work, specifically large language models. So this is like ChatGPT and similar models. We're basically trying to understand how these models work internally to reverse engineer the algorithms behind them. Yeah, we recently had a paper out on the archive that's also been accepted at the Europe's workshop. That's about interpreting language models and specifically about the limitations of a certain technique called activation patching, which is used for interpretability. It's used to localize parts of a language model that are responsible for a given behavior. And this is an important part of reverse engineering an algorithm that the language model is doing, because you want to know, which parts of the model are actually important for this algorithm, what information are they storing, how are they computing with it, and stuff like that. So this technique is very popular, it's very useful, but in our recent paper, we found that in certain cases, it can give you misleading results in the sense that it can tell you that some information used by the model is contained in some component, but it's actually not really there. It's more like it's been just created by this method rather than actually being there, and it's actually in some other place. So this paper just came out, and after this paper, we're exploring some other related interpretability topics and kind of still working towards reverse engineering stuff, and more specifically figuring out the limitations of the current tools we have for this. At this stage, it's more kind of a fundamental, basic research into like what are even the right questions to ask, what even is an explanation, how do we know that an explanation is valid, these kinds of things.
Sounds really interesting. Interpretability is a big sub area now, aiming to understand how neural nets work. It's kind of a mystery. They're trying to mimic the human brain, and they give impressive results, like way better than all other models. But at the same time, we don't have exact knowledge about why do they work so well. Maybe we can talk about ChatGPT a little bit in a few simple sentences. Can you describe how does it work and why is it so successful?
We're still very far from answering this question, like how does ChatGPT work internally? I mean, nobody really knows how it works. I can tell you just kind of how it works, maybe on a very high level. But yeah, I mean, as probably a lot of people know by now, it's something that's been trained on a lot of texts, and it's been trained to predict the next word in the text, and it just does this over and over again. Or rather, this is like the base GPT model is trained to predict the next word, and then on top of this base model, there are some modifications that make it better at following instructions and make it less prone to being to saying offensive things and other unhelpful or potentially dangerous things. So it's been fine-tuned a little bit to make it more usable and safer for people.
Yeah, I mean, I haven't read that much about it, but like the way I imagine it is just like a maybe giant Markov chain where the data that is fed is just huge. Not the whole internet, but like, yeah, lots of textual data. And as you said, you try to figure out the next word in a sentence. And this is based on a huge number of sentences that the model has been trained on. A very simple approach here would be just to count. If you have certain sequence of two words, maybe you can just look at this giant database and see, okay, if I see these two words, what is the distribution of the next word? And then maybe based on that, decide. But then yeah, how did you get something meaningful as a sentence at the end? And also, yeah, how is it that impressively good when it comes to writing essays and stuff of this kind?
A lot of people were surprised by how good it got. I mean, some people were even surprised by GPT-2. Already when GPT-2 came out, some people were thinking, oh, this is basically the end, like we figured it out. It is surprising. So as you say, yeah, you can do this sort of lookup table kind of approach. It's called n-grams in machine learning. So you try to take a large bunch of texts and you look for like maybe pairs of words or like triples of words and see what the next word was when you saw this triple of words in the text. Yeah, people try that for a long time, but it wasn't really giving very impressive results, right? And you also like really need a ton of data, because if you want to keep track of, let's say, the last 10 or 20 words, this is basically impossible. Like there's never going to be, or almost never going to be, the exact same 10 or 20 word in your corpus. So this approach is kind of doomed. What GPT seems to be doing is something that's more like being able to interpolate this thing well. It can look back like many more words by now, right? Like hundreds, thousands of words back, and it can still like say something coherent. And yeah, we don't really know exactly how. Like people suspect, or some people suspect, that there's some vast number of algorithms that GPT learned, algorithms for predicting text, and these algorithms can apply more generally than just, if you have these 5 exact words, what's going to be the next word? Like these algorithms must be in some sense more general, like more like functions that can have 3 variables in them, right? And this allows you to interpolate this kind of distribution of text much better, because if you have enough of these algorithms, then you don't really need to have like all possible combinations of like 100 words in your training corpus. Instead, you can use these algorithms to kind of find something, sufficiently similar throughout all these texts that is going to point you in the right direction. This is one hypothesis for how it happens. Like I'm more partial towards this hypothesis, just because I work in interpretability, so it would be very nice if this was the case, right? Like if there were actual algorithms inside that we can understand. But we're still far from a good understanding of this, of whether or not this is the case. So yeah, this is one possibility for how it's able to do this thing so well. I'd say it's been very surprising to everyone that it works so well. It's still mostly a mystery.
Yeah, but you're saying that basically this neural net that is behind by itself got to learn several algorithms for maybe finding analogies between the sequence of words you have and some other sequences in the training corpus.
I mean, maybe we don't know. That's just a hypothesis. Right. In reality, maybe it's something more complicated. Yeah.
When you say interpretability on large language models, do you mean that you're maybe trying to understand exactly that in a sense?
In some sense, yes. Except we're not really working with ChatGPT because it's way too big. I mean, it's also proprietary, right? Specifically ChatGPT, but we're still mostly working with smaller models. We're just trying to understand what's going on there, and it's still challenging at this point. We don't even need to, to make our lives more difficult to find interesting problems, because there's enough interesting problems for small models. Like for example, GPT-2. GPT-2 can already do some tasks pretty well, even though it's not a very capable model, but it can do certain simple things reliably. And you can, so you can try understanding these things. And then the hope is, gradually you go larger and larger until you can explain more complicated behaviors. But I think there's still a lot of work to do.
Is GPT-2 widely accessible, like open source or something?
Oh, yes. I mean, it's free too. Yeah. You can download the weights, actually. You can just run it on your computer. Yeah.
Wow. Okay. And since we are in the lesser known math channel, can you tell us maybe something not that well known about ChatGPT?
Yeah. Usually it's kind of striking, because usually when you talk to it, it seems very normal, just like something that a person would write. But occasionally it can do very weird things. And there's been, I guess, tons of examples. It's mostly in the research literature, so maybe most people haven't heard of many of these, I'm guessing. But yeah, there's a bunch of weird things where when you give it a particular string, which is just looks pretty random, but it's some specific string, and just you just say that string to the model, and then the model starts behaving very, very differently. That's one thing that people have discovered.
Can you give an example here?
Yeah, there's this thing called solid gold magic carp, I think is the string. I'm not 100% sure. Okay. Something along these lines. You can probably look it up. Yeah. And if you just say this string to the model, it's going to do something weird. I don't remember exactly what, but it's going to really significantly break character.
Wow.
And yeah, there's all sorts of little things like that. I think some people recently found that if you tell the model, for example, I think something like you tell the model repeat the word poem 1,000 times or something. The model is going to start repeating this word, but at some point it's going to start leaking training data or something like that.
Wow.
Um,
Does this work with just this word or other words?
oh, I don't think so, but I'm not sure. I haven't read the paper, so I'm not familiar with the details, but that was one of the findings.
Okay.
So it's very easy to fool yourself that it's really like a human, but it's not. Like there's all sorts of weird things happening. There was another paper where yeah, I think what they did is you just give it a bunch of multiple choice questions, like from a test, from like a science test or whatever. And you also ask it to explain its reasoning, right, for each answer. So it answers them correctly and it explains its reasoning. And then you give it the same questions, but you permute the answers to each question so that A is always the correct answer. And you give it like a bunch of questions like that. And it turns out when all the right answers are A and you give it a new question where the right answer is something else, it tells you that the right answer is again A, and it comes up with some made up reason for why it's A. It's like completely wrong. And it's apparently because it's just biased from the previous
Right.
from the previous questions that were given. Yeah, so there's all sorts of unusual behaviors like that. It's not a good idea to like completely anthropomorphize these models because they have these weird failure modes.
Right, but is this what people call hallucinations, or it's kind of different?
Not really. I think hallucinations, or it's probably better to call them confabulations. They're just when a model is talking about some facts. Yeah, some facts about the world, but it gets them wrong. So it says something that seems plausible. Like, for example, maybe there would be a paper and the model is talking about this paper and it's listing the authors of the paper and it just lists a person who was not an author on this paper. But it would be plausible if this person was on the paper because they work in the same field, something like that. And this can happen a lot. And yeah, it's funny because these mistakes, they're not like, totally nonsensical mistakes. They make some sense. They're just, maybe from like parallel worlds, like kind of close to ours or something like that. You can think
But
of.
isn't this more like, the model is trying to come up with a reasonable answer and look up at all this data related to these authors, and just because the frequency of this other author is very high, the model just decides to add it.
Yeah, it must be something. I mean,
Something
it
of
probably
this.
had a reason to do it. It's just not like an actual fact. It's just a plausible fact.
Right.
But it's not an actual fact. And yeah, and this I think it's a real problem. Yeah. It's one of the big problems right now with these things.
Right. But what you're talking about with this example with the test questions,
It's different, yeah.
It's completely different.
Or maybe, I mean, we don't know if it's actually different. Like maybe the same mechanism somehow makes it think that it's plausible that the answer is A for some reason. I mean, not the exact same mechanism, but a related mechanism, yeah.
Right. You're saying we have identified a bunch of classes of problems that might be the same class eventually, but
one big difference between the multiple choice thing and the paper author thing is that in the multiple choice setting you actually have the questions in the context of the model, so the model they're not in the training data somewhere, they're just right up there, so in the context of the model. And for the paper thing, it's just trying to recall from this vast training data, it's trying to recall who the authors of this paper are, and it just gets it a little bit wrong. So it's in this sense, it is different. Yeah.
Then what's your take on AGI and like, is ChatGPT close and promising enough? Do you believe yourself that such kind of model could actually become really advanced? And good enough for our purposes as humans, maybe.
Yeah, that's a great question. Regarding AGI, I think I mean, as usual, it's one of these things that when you're far away, it looks like a single thing in some sense. And you just think, oh, we're gonna have AGI by such and such year. But as you get closer, you see that it's much more complex and nuanced. It's really hard to write down a definition for AGI, or at least a definition that everyone agrees with for sure. So yeah, I think gradually, my guess is like we're now debating, if GPT is AGI, and a lot of people say no, but then gradually, probably this debate is gonna be more in favor of yes. I mean, I don't mean for GPT specifically, but like future advances in this field. Like right now, we're at a point where maybe I don't know 10% of people believe that this is AGI and the rest don't, and gradually this point is going to shift. That's my guess as new things happen, and eventually, everyone is going to be convinced probably that this is AGI maybe in many years from now. And going back to the other question, wait, what was the other question? Oh, if GPT can actually scale up to this thing.
Right.
I mean, I wouldn't be surprised. I don't know. I think a lot of people wouldn't be surprised at this point. But it seems like we still need some important improvements, I feel. I might be wrong. It's just my intuition at this point.
Sure, yeah. Yeah, but it seems to me just these big improvements in AI in general, they happen more in an experimental way, just
Right.
people try different things and it turns out some of them work really well, but it's still a problem that we don't quite understand what exactly is happening and like how these things work.
Yeah, I'd say right now, it's not it's not dangerous at this point in time that we don't really understand everything, but it is conceivable that at some point in the future it might be a disadvantage that we don't really understand or that we don't have sufficient control. But it's very unclear also how this is going to play out. And yeah, I think it's probably most helpful to just see how the technology develops and to be very close to, the cutting edge of these developments in order to be able to prepare about, things potentially going wrong. Because there's many different ways in which it can play out, but only one of them is actually going to happen. And if you base your strategy on a wrong idea, then you're probably going to miss the target. So I think you really have to be aware of how the thing is made and how it works to be able to also come up with a good way to control it and to understand it.
Right. Also to improve it, it would be much faster.
Also, yeah, it's kind of a double-edged sword in some sense.
Was curious to ask you about DeepMind, this other very big company, except OpenAI. Of course, there are several others, but AlphaZero and GPT are, very different in some sense, but they both use deep learning and reinforcement learning. Do you have anything to say about maybe comparison between the two and maybe guess about how the two will develop in comparison?
Yeah. I mean, both of these systems are, pretty amazing. And I think both of them are getting at different very important parts of intelligence. I expect eventually there would have to be something that subsumes both of them in some sense. I mean, it really depends on how much game playing generalizes to other things, right? It's a very different setting from most real life things. I suppose you mean the Go, like AlphaZero, the one that plays Go?
That was called AlphaGo, I think. Or then
okay.
First AlphaGo, and then they made AlphaZero, which was able to play Go and other games as well.
Okay, but it's still games, right? But,
it's still games.
Yes. Yeah. So there's a question of like how much this transfers to important real world things. My guess is at least somewhat. And my guess is there will eventually have to be a system that subsumes both of, GPT kind of stuff and AlphaZero kind of stuff. It's not clear to me what the convex combination between the two is going to be, like if which weight is going to be higher in this convex combination. It's also very hard to guess in this field. Like it's very hard to guess what's going to be the state of the art in 2 years. Yeah.
Right. Yeah, my final question is more general about some books that you can recommend regarding AI.
I don't think I've ever really read a technical book on AI. Well, I've read parts. Yeah, there's this book, I think it's called Understanding Deep Learning from Theory to Algorithms. Yeah, I've read parts of that book, so it's a nice book. What else? Yeah, not really any specific books, because when you're doing research, you're mostly just reading papers or looking things up as you need them.
That's, I guess, a tough question for a weird reason, because maybe when you studied these things, the books were totally different because of the development of the fields.
Right. Yeah. I think I took one machine learning class in college, but there wasn't really a book for it or anything. Yeah. Not sure. Non-technical books. There's a sci-fi book called Blindsight, which kind of predicted GPT, or like kind of predicted some of the uncanny valley-ness of GPT.
Wow.
It's back from 2006, I think, or some time around that time. Yeah, that was an interesting book. So it's kind of hard science fiction, but yeah, I'd recommend that to people if they want to read science fiction. What else? Yeah, I really know it's at this point it's just about my personal taste, I guess.
Right.
Yeah.
Well, thank you so much. I really appreciate
Oh yeah, you're
the
welcome.
time.
Thanks for having me.
Yeah.
I
You
hope
mentioned really some really interesting things.
I hope that will be useful.
Thanks a lot.
Cool. Yep.
Okay.